Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture Lecture Series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. I'm Philip Emeagwali. My contribution of the world's fastest computing to mathematical knowledge made it possible to invent a new computer and create new mathematics. In 1989, I was in the news for discovering how to harness the world's slowest processors and use those processors to solve the most difficult problems at the crossroad where new mathematics, new physics, and the world's fastest computing intersect. In algebra, the most difficult problem was to discover how to solve the largest system of equations arising when executing detailed computational fluid dynamics codes, such as global climate modeling or petroleum reservoir simulation, and executing those codes across the millions of processors that outline and define a supercomputer. In the 1970s and 80s, my mathematical quest was to become the first person that could solve such initial boundary value problems and solve them across the slowest processors in the world. At 8:15 in the morning of July 4, 1989, I discovered that the world's fastest computer can be built with the world's slowest processors. And I invented the supercomputer technology and did so across the slowest processors in the world. That new supercomputer paved the way and became the precursor of the world's fastest computer that now computes with millions of ordinary processors. Parallel supercomputing was my mathematical quest for how I can cross the new frontier of knowledge, of how to solve an unsolved system of equations in algebra. My quest was to cross that frontier and conquer today's mathematical challenges. My quest was to solve previously unsolved problems and quickly compute the most compute-intensive problems in large-scale computational fluid dynamics, such as simulating the spread of contagious viruses inside Japan's Tokyo subway, where 3.1 billion passengers a year are packed like sardines. In 1989, it made the news headlines that an African supercomputer genius that worked alone in Los Alamos, New Mexico, USA, has invented how to solve the largest system of equations in algebra and invented how to solve those systems by parallel supercomputing them or solving many equations at once and solving those equations across a new internet. That's a new global network of 65,536 coupled processors. I visualize my computing machinery as a small copy of the internet. I, Philip Emeagwali, is that African supercomputer scientist and the computational mathematician that was in the news in 1989. I was in the news for inventing how to solve the largest system of equations during the most important applications in algebra. One such application is in computational fluid dynamics. The poster girl of large-scale computational fluid dynamics is the supercomputer petroleum reservoir simulation that must be used to nail down the exact locations of crude oil and natural gas. Such extremely fast calculations can only be executed across an ensemble of millions of processors that occupies the space of a soccer field and that simulates an oil-producing field that's up to 7.7 miles or 12.4 kilometers deep. An oil field is about the size of Abuja, Nigeria. The Agbami oil field of Nigeria was discovered in late 1998. Agbami was Nigeria's second largest deep water oil field. Agbami is second to the Bonga oil field. Agbami oil field is located 4,900 feet or 1.5 kilometers away from the coastal shores of central Niger Delta. It has a peak oil production of 250,000 barrels per day. Why is the supercomputer important to Nigeria? 1 in 10 supercomputers were bought by the petroleum industry. The most powerful computer in the world costs the budget of a small nation. The fastest computer is the heavyweight champion in the world of petroleum technologies. The supercomputer is used to pinpoint deposits of crude oil and natural gas. Fastest computing is my contribution to modern algebra and to the petroleum industry. I'm the subject of inventor reports because I invented how to execute the world's fastest calculations and perform them across an ensemble of the slowest processors in the world and solve the most compute-intensive problems at the crossroad where new mathematics, new physics, and the world's fastest computing intersect. I invented how to solve the most compute-intensive problems and solve them across a new internet that's a new global network of 65,536 coupled off-the-shelf processors that shared nothing and that each operated its operating system. By 1986, I realized that the most difficult problem in petroleum reservoir simulation, namely the solution of a parabolic system of partial differential equations, was at its granite physical and mathematical cause an effort to forecast the weather, but to forecast it backwards in time. This backward technique is called hindcasting and is used to forecast, or rather to hindcast the weather and hindcast or reforecast up to 7.7 miles or 12.4 kilometers below the surface of the earth, and hindcast it across an oil-producing field that's up to twice the size of the state of Anambra, Nigeria. Because I was both a geologist of the late 1970s and a meteorologist of the early 1980s, I could translate that compute-intensive problem and translate it across physics, calculus, algebra, and computer science, and translate it from the primitive equations of meteorology to the 9 Philip Emeagwali equations of mathematical geophysics. This new field of study is described as the subsurface porous media multi-phased fluid flow modeling, executed across millions of off-the-shelf processors that were identical and coupled. In 1989, I could solve the most difficult problem arising in supercomputing. I solved it by deeply understanding and drawing on the mathematical metaphors between the extreme-scaled computational fluid dynamics problems in both meteorology and geology. My contributions to mathematics had their calculus and algebra roots on how I reformulated the hardest problem in subsurface geology. I reformulated that mathematical problem and did so in a meteorological context. Furthermore, I parallel processed that mathematical problem, and I did so across a then world record ensemble of 65,536 processors. Not only that, I visualized those processors as outlining and defining a small internet, and as tightly circumscribing a globe and encircling that globe in the manner computers encircle the earth. My 1989 discovery changed the way mathematicians solve their most compute-intensive problems. In my new way, the most difficult problems in physics, mathematics, and computer science are solved across an ensemble of millions of processors instead of within one processor, as was done in the old way. The toughest problems in mathematics are solved on supercomputers purchased for the Nigerian petroleum industry. The prototypical most difficult problem in supercomputing was to compute at the fastest speeds the motions of crude oil, injected water, and natural gas that were flowing across an oil-producing field that's up to 7.7 miles or 12.4 kilometers deep. An oil field is about the size of my hometown of Onitsha, Nigeria. The Bonga oil field is located off the Nigerian coast and 75 miles or 121 kilometers southwest of the Niger Delta. The Bonga oil field was underneath an average water depth of 3,300 feet or 1 kilometer and covers 60 square kilometers and produces both crude oil and natural gas. The Bonga oil field began production in November 2005 and was projected to be abandoned in the year 2022. In the 1950s, 60s, and 70s, mathematical physics textbooks classified the governing system of coupled, nonlinear, time-dependent, three-dimensional, and state-of-the-art partial differential equations as parabolic. Often, when parabolic partial differential equations are discretized to yield a system of partial difference equations, the resulting system of equations of computational linear algebra is tridiagonal. Its associated tridiagonal matrix has non-zero elements on the main diagonal and on the two diagonals below and above the main diagonal. Why was my contributions to mathematics in the news in 1989? My contribution to mathematics was this. In the 1980s, I changed the way we look at the calculus and the algebra behind the compute-intensive simulations of the motions of crude oil and natural gas that were buried 7.7 miles or 12.4 kilometers deep and buried across an oil field that's about the size of a town. My mathematical discovery was that the world's fastest computer can be built with the world's slowest processors. My invention was the cover story of top mathematics publications, including the May 1990 issue of the Science News, which was the flagship publication of the Society for Industrial and Applied Mathematics. I'm the subject of school essays on famous mathematicians because I changed the way mathematicians solve their most compute-intensive problems in algebra. My contribution to the mathematical knowledge and supercomputer technology used to nail down the exact locations of crude oil and natural gas is this. I paradigm shifted from a parabolic system to a hyperbolic system of partial differential equations that governs the initial boundary value problem. And I paradigm shifted again from tridiagonal to diagonal system of equations of computational linear algebra. From the parabolic and hyperbolic systems, respectively. I invented the system of equations of computational linear algebra that must be used to recover otherwise unrecoverable crude oil and natural gas. In 20th century algebra, such systems were most often tridiagonal. Such tridiagonal systems are unsolvable in parallel or impossible to solve by dividing each into a million or even a billion lesser compute-intensive problems that can be mapped onto as many processors and then solved with a one-to-one correspondence and solved at once or in parallel. Because I was computing and communicating across a global network of 65,536 processors, I saw computational mathematics differently. Because I saw mathematics differently, I thought differently and invented differently. Why did I invent the 9 Philip Emeagwali equations? My original derivations of the 9 Emeagwali equations are lengthy. However, they are fully described in my YouTube channel named Emeagwali. In essence, my point of departures from the mathematical derivations of Darcy's equations that govern subsurface geophysical fluid dynamics were that I accounted for both the temporal and the convective inertial forces. I've posted the mathematical details across my 1,000 video clips that I've also posted on YouTube. For clarity, I detailed my mathematical derivations in closed caption prose. My mathematical quest was to discover how to solve the differential initial boundary value problem, not for how to solve the algebraic discrete problem from that initial boundary value problem. My quest wasn't for how to solve the initial boundary value problem and solve it as an applied mathematician who solved it on his blackboard. That quest for an extremely fast computer was for how to solve the never before solved larger scale problems in computational linear algebra and solve them as a modern computational mathematician who is sitting astride his global network of 64 binary thousand motherboards. Each motherboard was a computational metaphor for his as many or 65,536 blackboards. I invented a system of 9 partial differential equations of calculus and then invented my 9 partial difference algorithms, or the complete step-by-step instructions each of my 65,536 processors must execute as the condition for solving the difficult mathematical problem and solving it at the world's fastest speed that made the news in 1989. I used my new algorithms to discretize my system of partial differential equations, which in turn yielded my system of 24 million equations of computational linear algebra. Those were the longest equations in the mathematics of 1989. With my new algorithms, those equations became diagonal instead of tridiagonal. It's impossible for my new system of 24 million diagonal equation of algebra and the old system of 24 million tridiagonal equations of algebra to be mathematically equivalent. I visualize my problem as identical twin problems of algebra. The diagonal and the tridiagonal systems of equations of computational linear algebra arose from different initial boundary value problems with the same boundary condition, the same initial condition, and the same mathematical and physical domains. However, each initial boundary value problem had a different governing system of partial differential equations at the frontier of calculus. The diagonal and the tridiagonal systems of equations of computational linear algebra are equivalent in their physical essences, and they are equivalent in the physical sense that both arose from a hyperbolic and a parabolic system of coupled, nonlinear, time-dependent, three-dimensional, and state-of-the-art partial differential equations, respectively. Both systems of partial differential equations of calculus encoded the same set of laws of physics. My new diagonal and the old tridiagonal systems of equations of computational linear algebra approximated the same difficult mathematical problem of extreme scale computational physics. My new diagonal and the old tridiagonal systems of equations of computational linear algebra are as different as identical twins from the same egg and sperm and from the same genetic materials. Just as identical twins are clones, my new diagonal and the old tridiagonal systems of equations of computational linear algebra were clones. They are not algebraically equivalent, but they arose from the same difficult mathematical problem of extreme scale computational physics. Metaphorically speaking, they arose from the same egg and sperm. Scientifically speaking, they arose from the same set of laws of physics. My invention of fastest computing, which occurred on the 4th of July 1989, changed the way mathematicians solve the most compute-intensive problems in algebra. The cover stories of mathematics news journals read by leading mathematicians celebrated my mathematical discovery as a breakthrough that makes it possible for high-performance computational mathematicians to achieve speeds in supercomputing previously considered impossible. In 1989, mathematicians celebrated my discovery of the fastest computing, and did so because it heralded the end of their old arithmetic paradigm of solving one compute-intensive problem at a time. And it marked the beginning of the new paradigm of concurrently solving millions of sets of compute-intensive problems and solving them at once. On the 4th of July 1989, I achieved a supercomputer breakthrough. I used the 65,536 slowest processors in the world to reduce 65,536 days or 108 years of time to solution to merely 1 day of time to solution. Furthermore, I discovered that the most compute-intensive problems in algebra that in turn arose from calculus could be solved across a new internet. Not only that, I invented that new internet as a new global network of 64 binary thousand processors that were coupled. Each processor had its dedicated memory that shared nothing, but were in dialogue with each other. My high-performance computing experiment, which I conducted across a new internet, that's a new global network of 65,536 processors, led to my discovery that elucidated why the world's fastest computer must be powered by billions of processors. The reason my discovery of how to execute the world's fastest computing was in the June 20, 1990 issue of the Wall Street Journal was because it opened the door to the fastest supercomputers that were powered by over 10 million processors. I discovered how the oil and gas industry now harnesses the fastest computing from the slowest processors and do so to nail down the locations of subterranean hydrocarbons. My discovery that millions of processors can be used to solve the most compute-intensive problems is the new knowledge used throughout the petroleum industry. It's the most critical technology now used to pinpoint deposits of crude oil and natural gas and used to recover them. It's used from the producing oil fields of Nigeria to the oil fields of Angola. I used the largest system of equations of algebra that defined the most compute-intensive problems in physics as the backdrop for my experiments across my ensemble of 65,536 processors. I used those equations as my supercomputer testbeds. In the 1970s and 80s, fastest computing across the slowest processors existed only in the world of science fiction. My contribution to computer science was that I challenged the established truth and turned that science fiction to reality. That truth was the widely held belief that the slowest processors in the world cannot compute together and do so to solve the most compute-intensive problems in algebra and in extreme-scale computational physics. and solved them at the fastest recorded supercomputer speeds. The recognitions which I received from the supercomputing community in 1989 and later was the first time such skepticism over parallel supercomputing was overcome. In the 1970s and 80s, 25,000 supercomputer scientists tried to parallel process and do so across processors and computers. They gave up. They dismissed my attempts to solve the most difficult problems via parallel processing as impossible. I proved them wrong. In an often cited paper published between April 18 to 20, 1967, the IBM supercomputer designer, Gene Amdahl, formulated Amdahl's law. Briefly, Amdahl's law predicted that supercomputing across the slowest processors will forever remain an enormous waste of everybody's time. Seymour Cray designed 7 in 10 supercomputers sold in the 1970s and 80s. Seymour Cray agreed with Gene Amdahl. Using the chicken as his metaphor for the slowest processor and the ox for the fastest processor, Seymour Cray asked the supercomputing community his famous question: if you were plowing a field, which would you rather use? 2 strong oxen or 1,024 chickens? Regarding the ox versus a billion chicken debate, I visualize the grand challenge problem of supercomputing as breakable and chopped up into 1 billion less challenging problems, each akin to a few wheat seeds in a large field. My theory was that a billion hungry chickens can eat up 1,000 billion wheat chickens and eat them faster than 1 hungry ox. Parallel computing is a century-old theory that existed in the realm of science fiction. My contribution to computer science made the news because my invention of the first supercomputing across the world's slowest computers turned that science fiction to reality. On the 4th of July 1989, the century-old theory of harnessing 64,000 human computers became timeless and new again. It was never old. When I came of age in the 1970s, the computer world was the mouthpiece of the information technology industry. A state-of-the-art survey published in the June 14, 1976 issue of the Computer World quoted the leaders of thought in the world of supercomputers as unanimously agreeing that harnessing thousands of processors will be too, quote-unquote, large and clumsy. The title of that Computer World article summed up the skepticism towards parallel processing and my later discovery of the world's fastest computing across the world's slowest processors. The pessimism was embedded into the title of that article, which was, quote, Research in Parallel Processing, questioned as waste of time, unquote. My discovery made the news because it was computing's equivalent of breaking the sound barrier to create a sonic boom. Before my discovery, fastest computing across slowest processors was an intellectual barrier that no human dared to cross. I was in the news because I was the first person to cross that intellectual barrier. I was the first person to scale the pinnacle known as the world's fastest computing. On July 4, 1989, I became the first person to plant his country's flag in the then unknown territory of the supercomputer as it's known today and as it's expected to be known tomorrow. I used 65,536 processors to demonstrate how a mammoth supercomputer can be built from a billion processors. I discovered how harnessing up to a billion processors will enable the world's fastest computer to have the horsepower it will need to address the grand challenges of the scientific world. I researched as a lone wolf because my supercomputing milestone was believed to be unachievable. Parallel processing powers every supercomputer manufactured today. The supercomputer is to science what the microscope is to biology. My scientific discovery, which occurred on July 4, 1989, was that the world's slowest processors can be used to solve the most compute-intensive problems in science, engineering, and medicine. My discovery of the central essence of the world's fastest computers made the news headlines because it changed the way we look at the modern computer. I discovered how to reduce 180 years of time to solution of the most difficult problems in large-scale algebra and computational fluid dynamics, and how to reduce that time to 1 day of time to solution. In the 1970s and 80s, I was mocked, ridiculed by vector supercomputer scientists, and offhandedly dismissed because I claimed to have discovered how to reduce the times to solution of the most compute-intensive problems, such as the high-stake global climate models, and reduce them by a factor of 1 billion across a new internet that's a new global network of 1 billion processors that shared nothing. I was mocked for claiming my discovery of the world's fastest computing and claiming it when it was considered impossible to reduce those times to solution and do so by a factor of 8. When confronted with such a compute-intensive problem, the vector supercomputing community joined ranks and tore holes in my then unsubstantiated theory. I theorized that the slowest processors could be harnessed and used to compute faster than the fastest supercomputer. My unorthodox approach to solving compute-intensive problems is called parallel supercomputing. Until my experiment of July 4, 1989, the parallel supercomputer was not a the parallel computer was not a supercomputer. It was then a million times slower than the supercomputer. In 1989 and in Ann Arbor, Michigan, my character was malign because I was conducting research on parallel supercomputers, a technology then dismissed as pseudoscience. I distributed 6 copies of my 1,057-page supercomputer report to scientists in Ann Arbor, Michigan. All 6 copies were thrown into the wastebasket. To their surprise, a few weeks later, it made the news headlines that I had won the equivalent of the Nobel Prize in supercomputing. I won that prestigious prize for my supercomputer invention, which I fully described in my 1,057-page research report that they're trashed into the wastebaskets of Ann Arbor, Michigan. After I won what was referred to as the Nobel Prize of Supercomputing in 1989, the intellectual fireworks exploded. I didn't kill any person, yet I was subjected to a Galileo trial that was computing's equivalent to the O.J. Simpson trial. If they were to accept my discovery, they must forget many things they've learned, such as their belief in white intellectual supremacy. I solved the most difficult problem at the crossroad where new mathematics, new physics, and the world's fastest computing intersected. That accomplishment was the reason I was compared to the likes of Albert Einstein, Pythagoras, and Euclid. In retrospect, and for racial and intellectual reasons, I was not taken seriously as a black mathematician who was equally at home in physics and computer science. I was confident because, as far as I knew, I was the only person in the world that devoted almost the entire decades of the 1970s and 80s to supercomputing across processors. I acquired the specific sets of skills and knowledge within mathematics, physics, and computer science that in turn would have enabled me to solve the most difficult problems in supercomputing. First, I was black and African, and therefore grossly underrated with respect to Albert Einstein. Second, I was a lone and unsalaried supercomputer scientist whose research was grossly undervalued by both the funding agencies and the prize committees. They automatically rejected my submission. They automatically rejected any submission from a black African scientist. Third, I was misperceived as only a one-dimensional mathematician or physicist, never as a three-dimensional polymath or a triple threat that was at home in computer science. Fourth, it was not widely known that I had been continuously supercomputing since June 20, 1974, on one of the world's fastest supercomputers that was at 1800 Southwest Campus Way, Corvallis, Oregon, USA. Fifth, I was also trained as an astronomer, meteorologist, and geologist. Therefore, I was not timid about crossing disciplinary boundaries and doing so when pursuing the elusive answer to the biggest question in supercomputing. That question was this: how do we compute fastest with the slowest processors? In supercomputing, the most compute-intensive problem must be breakable into a billion pieces that can be solved at once and solved across a billion processors that each was self-contained and shared nothing. Solving the most difficult problem across the world's fastest computer is like putting a jigsaw puzzle with a billion pieces together. My invention of how to compute in parallel or compute many things at once was mentioned in the June 20, 1990 issue of the Wall Street Journal. It took me the prior 16 years to discover how and why computing across the slowest processors makes the fastest computers fastest. My discovery opened the door that elevated the parallel supercomputer to a new supercomputer that's up to a billion-fold faster. and that's used to solve the larger system of equations in many fields. Such grand challenge problems range from computational fluid dynamics to computational medicine, such as simulating the spread of contagious viruses across Onitsha market where social distancing rules are not enforced. In the 1980s, there were 25,000 computational mathematicians who also desired to know how and why a multitude of processors makes the slowest computers faster and makes the world's fastest computer fastest. The reason those mathematicians gave up on massively parallel processing was because their textbooks warned them that supercomputers built with a billion processors will forever remain an enormous waste of everybody's time. If any of those mathematicians or physicists or computer scientists had the knowledge that I had, they would have been famous for solving the most difficult problem in supercomputing that I solved in 1989 and that made the news headlines. Because everybody ridiculed and rejected the theory of solving many problems at once, parallel supercomputing was abandoned. That was how I became the lone full-time programmer of 16 of the most massively parallel supercomputers ever built. Today, the most powerful supercomputer hosts up to 10,000 programmers. What differentiates I and the other 25,000 vector supercomputer programmers of the 1980s were these. I invented how to harness an ensemble of 65,536 off-the-shelf processors that were coupled and that shared nothing. In 1989, it made the news headlines that an African supercomputer genius in the USA had invented how to harness 65,536 processors and invented how to use them to solve the most compute-intensive problems called grand challenges. Such problems arise when addressing some of the world's biggest problems, such as simulating the spread of COVID-19. My invention opened the door to the technique of parallel and distributed algorithms and the companion technology of the massively parallel supercomputer. Parallel computing is the core knowledge that makes the impossible to solve possible to solve and makes it possible to solve up to a billion mathematical problems at once. I, Philip Emeagwali, was that African supercomputer scientist in the news in 1989. The grand challenge of computing was to be the first person to solve the most difficult problem and solve them at the world's fastest speeds, but solve them across the world's slowest processors. A reason it was called a grand challenge problem was that the 25,000 vector supercomputer scientists of the 1980s and earlier couldn't solve it. The reason vector supercomputer scientists couldn't experimentally invent fastest computing across the slowest processors was that they were merely reading about how it's impossible to harness 65,536 processors. In the 1980s, it was believed that it will forever remain impossible to harness millions of processors and use them to cooperatively solve the most compute-intensive problems at the frontiers of knowledge in science, engineering, and medicine. those 25,000 naysayers had the opportunity I had to solve the most compute-intensive problems, which were central to supercomputing. All they needed was the brain power. Each of those 25,000 vector supercomputer scientists knew that the invention of supercomputing across the slowest processors would be akin to discovering a gold mine. My contribution to the development of the supercomputer is the reason I'm the subject of school essays on inventors and their inventions. I'm Philip Emeagwali. In 1989, I was in the news because I contributed the world's fastest computing to mathematical knowledge. That contribution changed the way mathematicians solve some of their most difficult problems. In their old way, the solution of the most difficult problem in computational mathematics was unsuccessfully tackled on the blackboard or one processor. In my new way, such problems are solved across up to 1 billion processors. I'm Philip Emeagwali. On July 4, 1989, I became the first person to cross the boundary of human knowledge of the world's fastest computing across the world's slowest processors. Those processors encircled a hyperglobe in the 16th dimensional hyperspace and did so in the manner the internet encircles planet Earth. That was how I invented the first internet, that is a global network of 65,536 processors. What is Philip Emeagwali known for? I discovered how to combine computers into a supercomputer that's an internet. That discovery is like a light from an ancient sky. I'm the only father of the internet that invented an internet. The supercomputer of today is radically different from those of the 1980s and earlier. Back then, supercomputers were powered by only one processor. Each was the size of a refrigerator, and it cost up to $40 million each. The world's fastest computer of today can be powered by up to 1 billion processors. It occupies the footprint of a football field, and it costs 40% more than the mile-long Second Niger Bridge in Nigeria. I invented the world's fastest computing as we know it today. In 1989, I was in the news for discovering that the slowest processors could be used to solve the biggest problems and find their answers at the fastest speeds. The fastest computer is why you know the weather before going outside. The reason I was in the news for my contributions to fastest computing was this. I discovered that some compute-intensive problems that were impossible to solve with one processor could be solved across an ensemble of 1 billion processors. That's how the supercomputer is used to track how the coronavirus disease spreads. That was the audacity of my world's fastest computing that occurred on July 4, 1989, and that made the news headlines. The inspiration that led to my scientific discovery of how and why using 1,000 processors makes the new supercomputer the fastest came from my mathematical investigations of the rates of error growths that occur while solving the largest systems of equations in algebra. Error growths occur while executing the most compute-intensive set of floating point operations of arithmetic. Floating point operations arose from finite difference equations of computational linear algebra. Finite difference approximations arose from discrete approximations of partial differential equations that govern initial boundary value problems arising at the frontier of calculus. My inspiration to compute at the fastest recorded speeds arose from the need to execute the most compute-intensive mathematical operations. Such operations arose from the need to solve the largest system of equations of algebra. Such large-scale algebra arose from the need to discretize the partial differential equation at the frontier of calculus. Such abstract calculus arose from the need to encode some laws of physics and chemistry that govern the 20 most difficult problems in supercomputing. The poster child of the most difficult problems in supercomputing is the extreme scaled computational fluid dynamics codes that must be used to simulate the spread of a once-in-a-century global pandemic. The supercomputer must be used to simulate the spread of virus droplets among the billions upon billions of train passengers around the world that are packed like sardines. The fastest computer is used to simulate ways of stopping the spread of contagious viruses. The world's fastest computer is used to solve unsolved problems that are important to society. I began supercomputing on June 20, 1974 in Corvallis, Oregon, USA. At that time, I described myself as a mathematician who is a number theorist. My high-performance computing started as a hobby, not a serious profession. Back in Onitsha, Nigeria of the early 1970s, I conducted independent research on Pythagorean triplets. Each triplet was an integer solution of the equation a squared plus b squared equals c squared. In the 1970s, I gradually shifted my research interest from number theory of pure mathematics to numerical analysis of applied mathematics to large-scale computational fluid dynamics, and finally to massively parallel supercomputing that's executed across up to 1 billion processors. I visualized my 65,536 processors as encircling a hypersphere in 16-dimensional hyperspace and encircling it in the manner the internet encircles the earth. The mathematical fields of number theory and numerical analysis are almost diametrically opposite. Number theory is abstract and is investigated on the blackboard. On the other hand, numerical analysis is applied and investigated on the motherboard. Number theory demands precise solutions and is used to invent encryption algorithms. In contrast, numerical analysis accepts approximate solutions of partial difference equations arising in computational physics. Since the equivalence theorem was discovered in 1954, research computational mathematicians investigating the discrete solutions of partial differential equations indirectly prove convergence, and did so by only proving consistency and stability. By convergence, I mean that As my grid spacing tends to 0, my solution of my system of partial difference equations converges to the exact solution of my system of partial differential equations that I discretized. In 1981, and a few years after, and in College Park, Maryland, I did extensive consistency and stability analysis. That is, I theoretically and experimentally investigated the rates of propagation of numerical errors that arise when the algebraic computations advance from one time step of finite difference approximations to the next time step. I knew in advance that my approximations to the originating partial differential equations are stable if and only if the errors introduced at any time step were not amplified at later time steps, but were reduced at subsequent time steps. In my stability proofs, I computed for the norms of the solution. The stability proof, the theoretical proof of the stability of finite difference approximations of real-world partial differential equations are impossible to prove. Instead, I proved the stability of a quote-unquote closed problem and then confirmed the stability of the complete partial difference approximations, and do so by coding and testing the numerical solutions. From my linearized stability analysis, I mathematically discovered that I'll do fewer computations if I started from first principles or start from the second law of motion in physics textbooks, and do so to rederive the governing system of coupled, nonlinear, time-dependent, three-dimensional, and state-of-the-art partial differential equations of calculus. Such equations govern the flows of crude oil, injected water, and natural gas that's often flowing up to 7.7 miles or 12.4 kilometers deep and across an oil-producing field that's about the size of Baltimore, Maryland. I mathematically discovered that when I include the temporal and the convective inertial forces, then the governing partial differential equations become hyperbolic rather than parabolic. From my linearized stability analysis, I mathematically discovered that I'll do fewer computations if the discretizations or reduction from infinite to finite of the governing system of partial differential equations to an approximating system of partial difference equations were explicit rather than implicit. In 1981, my big question was to figure out how to bypass the two vexing limits in physics and computer science that were known as Darcy's law and Amdahl's law, respectively. From my linearized stability analysis, I mathematically discovered how to bypass the constraint that was imposed by Darcy's law. That constraint limited the execution times of computational fluid dynamics codes that were governed by that Darcy's law and bypassed the perceived Amdahl's law limit of the maximum speed increase of a factor of 8. That was how I addressed the vexing limit of Darcy's law that could make my world's fastest computing less efficient and more compute intensive. That was how I addressed the vexing limit of Amdahl's law on the speedups across the millions of processors powering the world's fastest computer. From my linearized stability analysis, I learned that my diagonal system of equations of algebra arose from conditionally stable and explicit finite difference algorithms, while my tridiagonal system of equations of algebra arose from unconditionally stable implicit finite difference algorithms. In the practical terms of large-scale, high-performance supercomputing, implicit methods allowed larger time steps, which are more efficient, but implicit methods only allow sequential calculations, which are slower to compute. I discovered that implicit methods that yield a system of tridiagonal equations of algebra yield longer times to solution than explicit methods that yield a system of diagonal equations of algebra. I discovered that it's possible to solve the system of diagonal equations of algebra and solve them in parallel, or by solving them at once at 65,536 processors, or to at once solve the diagonal system and solve them across my new internet. I invented that new internet as my new global network of 65,536 processors that were identical and equal distances apart. As correctly explained in textbooks on computational linear algebra, it's impossible to directly reformulate a system of tridiagonal equations and reformulate that system into an equivalent diagonal system. That was my motivation for reformulating both systems of diagonal and tridiagonal equations, and reformulating them to solve the same initial boundary value problem, particularly those in large-scale, high-fidelity computational fluid dynamics, such as petroleum reservoir simulations. In the 1970s and 80s, my dream of discovering the world's fastest computing across the world's slowest processors was ridiculed as wonderfully useless. The reason I conducted my world's fastest computing research alone was because supercomputing across the slowest processors was mocked and dismissed as a vacuous gimmick. In the 1970s and 80s, the conventional wisdom in supercomputing was this: quote, solve one problem at a time and solve that problem as fast as possible, unquote. In an article dated September 2, 1985, the president of Cray Research Incorporated, the company that manufactured 7 intense supercomputers, described his company's attempt to harness 64 processors as quote unquote more than we bargained for. My mathematical quest began as an abstract speculation of a lone mathematician in 1974, Corvallis, Oregon, USA. That speculation was on the pure logic of differential calculus and in the compute intensiveness of large-scale algebra. The precondition to discovering my world's fastest computing was that I, first and foremost, also discover how to efficiently map my codes across up to 1 billion processors. My quest for the world's fastest computing continued as the rigorous analysis of 65,536 computer codes, which were developed with my one code to one processor mapping and correspondence. That mapping was to the as many processors that outlined and defined my new internet. That's a new global network of 65,536 processors. I invented how to make the otherwise impossible to solve possible to solve. Such mathematical problems arise when attempting to solve the largest systems of equations in the computational linear algebra of petroleum reservoir simulation. I discovered how to solve the most difficult problems arising in mathematical physics and solve them across the millions of processors that outline the fastest supercomputers. I invented how to solve the most compute-intensive problems in computational fluid dynamics and how to solve them across a new internet that's a new global network of 65,536 processors. I'm the mathematician who invented how to do more computations and do the most computations in 1 second on the supercomputer and do more computations than what every person on planet Earth can compute during every second of every day for 1 year. I did the impossible by reformulating my system of equations of computational linear algebra that were tridiagonal, that couldn't be solved in parallel or solved across an ensemble of billion processors. And by reformulating that system from the governing second law of motion in physics textbooks and the governing partial differential equations, or PDEs, of calculus that encoded that law, and discretizing and solving my system of PDEs as a system of diagonal equations of computational linear algebra that solves an equivalent problem that could now be solved in parallel. I didn't reformulate my system of equations directly. I reformulated them indirectly. My systems of diagonal and tridiagonal equations each arose from the same detailed petroleum reservoir model. To recover otherwise unrecoverable crude oil and natural gas only required that we use the laws of physics to simulate the petroleum reservoir. It didn't require that we solve a specific system of tridiagonal equations of algebra and solve it by or in itself. How did I invent 9 new partial differential equations of calculus and invent them from the second law of motion of physics that was discovered 3 centuries and 3 decades ago? To make such an invention demanded that I be a polymath, not a mathematician alone. The polymath, that's a triple threat in physics, mathematics, and computing, focuses on solving the most difficult problem in computational mathematics and solving it as a holistic whole. Often the mathematician is limited to only solving the algebra problem. Often the mathematician forgets that mathematics is a tool and a means to an end, not the end itself. That algebra problem was derived from the physics problem. I discovered a different path to simulating the motions of crude oil, injected water, and natural gas flowing up to 7.7 miles or 12.4 kilometers deep and across an oil-producing field that's often the size of Lagos, Nigeria. I discovered how to simulate the petroleum reservoir and do so a billion times faster, and by returning to first principles, which were the set of laws of physics and chemistry governing the motions of the crude oil, natural gas, and injected water flowing across reservoir rocks. I began from the top and from the second law of motion of physics, and did so to enable me to correctly rederive the governing system of 9 coupled, nonlinear, time-dependent, three-dimensional, and three-phased partial differential equations of calculus. My new governing system of partial differential equations is hyperbolic and represents a new paradigm in calculus. The old governing system of partial differential equations is parabolic and represents an old paradigm in calculus. My new governing system describes the three-dimensional motions of crude oil, injected water, and natural gas flowing across a highly anisotropic and heterogeneous oil field. The new system of coupled nonlinear 9 Philip Emeagwali equations describes the motions of fluids through an oil-producing field and along 3 spatial directions. By 1989, I had discretized those partial differential equations to yield a new system of 24 million diagonal equations instead of the old system of 24 million tridiagonal equations. Both were the longest systems of equations ever solved in algebra, and that is one of my contributions to how to solve the largest systems of equations of computational linear algebra from petroleum reservoir simulation, and how to solve them across a new internet that's a global network of processors that were coupled and that shared nothing. Since June 20, 1974, in Corvallis, Oregon, USA, my quest for the world's fastest computing was to invent how to solve the most compute-intensive problems in linear algebra. I invented how to solve them across a new internet, and I invented that new internet as a new global network of processors that were identical and that I visualized as equal distances apart. Since the late 1940s, the method of choice among computational mathematicians that try to solve the most difficult problems in subsurface geophysical fluid dynamics was called the alternating direction implicit method, or the ADI method. The ADI method was used to discretize a system of coupled, nonlinear, time-dependent, and 2 or 3-dimensional partial differential equations. Such equations were classified as parabolic. They govern the subterranean flows of crude oil, injected water, and natural gas. In the 1950s, 60s, and 70s, the alternating direction implicit method was widely used to formulate a set of systems of tridiagonal equations that arise from finite difference discretizations of the system of partial differential equations that governs the subsurface motions of fluids flowing up to 7.7 miles or 12.4 kilometers deep below the surface of the earth. In 1981, I discovered that it would be impossible to solve in parallel a system of tridiagonal equations in large-scale algebra and solve that system by dividing it up to 1 billion lesser challenging problems that in turn could then be solved with a one-problem-to-one processor mapping and correspondence, and solved at once and across an ensemble of up to 1 billion processors. I discovered that it will be impossible to solve a system of tridiagonal equations and solve it by synchronously emailing equal-sized subsystems of that system and emailing my subsystems across my 1,048,576 bidirectional regular and short email wires. Likewise, I visualize those email wires as being equal distances apart. Furthermore, I visualize my email wires as marrying my global network of the slowest 65,536 processors in the world, and doing so to emulate one seamless, coherent, and gigantic super-fast processor that's a virtual supercomputer. As the lone programmer of my virtual supercomputer, I visualize those processors as married together as one coherent unit. That's not a supercomputer by itself, but that's a new internet de facto. I discovered that it will be impossible to evenly distribute equal subsystems of my system of tridiagonal equations and distribute those subsystems across each of my 65,536 identical and coupled processors. Each processor operated its operating system and had its dedicated memory. Because it's impossible to solve a system of tridiagonal equations and solve it in parallel, I formulated an equivalent system of 24 million diagonal equations that approximated a more accurate system of 9 new partial differential equations which I invented, and that solves the same petroleum reservoir problem, or solves the same initial boundary value problem with different governing partial differential equations that differently encoded the same laws of physics that's at the physics core of the petroleum reservoir simulator. My mathematical beginning from a system of parabolic partial differential equations to inventing that system as a more accurate system of hyperbolic partial differential equations, and my formulation of a system of tridiagonal equations that approximated my parabolic partial differential equations, and my formulating of that system as a system of diagonal equations that approximated my hyperbolic partial differential equations, were mathematical inventions in calculus. That invention, or new mathematics, or my finite difference discretizations of the 9 Philip Emeagwali equations, changed the way we understand or solve the most compute-intensive problems that arise when simulating the flows of crude oil, injected water, and natural gas flowing across a highly anisotropic and heterogeneous producing oil field. A typical oil field is located 6,000 feet or 1.83 kilometers below the surface of the earth. But it can be up to 7.7 miles or 12.24 kilometers deep. My contributions to the physics used to pinpoint deposits of crude oil and natural gas were these. I discovered how to harness the millions of processors that power the world's fastest computer, and how to use them as one coherent computing machinery that emulates the world's fastest processor, that's 1 million times faster than a single processor solving the same problem alone. The grand challenge of petroleum reservoir simulation was to compute the flows of crude oil and natural gas flowing from a water injection well to nearby producing wells. By making the news headlines back in 1989, my invention changed the way we execute the mathematical calculations in extreme scale computational physics. It changed how mathematicians solve the most compute-intensive initial boundary value mathematical problems, such as those arising in computational fluid dynamics. It changed how mathematicians solve them in parallel and solve them by distributing them across an ensemble of processors instead of solving them in sequence or solving them only within one isolated processor that's not a member of an ensemble of processors. My invention opened the door to how to solve the most compute-intensive mathematical problems and solve them across an ensemble of millions of processors and solve them when the governing system of equations of algebra had its non-zero entries only along its diagonal. My contributions to high-performance computational physics led to the discarding of the old way of solving the field's most difficult problems, to the new way of solving those problems across an ensemble of up to 1 billion processors. In the traditional way, physicists solve their toughest and their most compute-intensive initial boundary value problems in computational physics and solve them in sequence, or solved one problem at a time and solved that problem within one isolated processor that wasn't a member of an ensemble of processors that communicates and computes together, and do both as one seamless, coherent, and gigantic supercomputer. In my new way, mentioned in the June 20, 1990 issue of the Wall Street Journal and in cover stories of top mathematics news journals, I invented how to solve 65,536 initial boundary value problems of computational fluid dynamics, such as the detailed global climate modeling, and solved them at once. In 1989, I was in the news because I invented how to solve the most difficult problems arising in physics and mathematics and solved them in parallel. And I invented how to solve them across an ensemble of 65,536 coupled processors. My signature contribution to supercomputing is this: I put to rest the saying that the world's fastest computing across the world's slowest processors is a beautiful theory that lacked experimental confirmation. As a research supercomputer scientist who came of age in the 1970s and 80s and in the USA, the most important lesson that I learned was that you can't become a genius in supercomputing without foremost applying quote-unquote sitting power. I sat the longest in front of the massively parallel supercomputer of the 1980s that is in reality the supercomputer of today. That's the reason my lectures or my contributions to computing, mathematics, and physics are by far the most extensive ever posted on YouTube. The reason I could post my 1,000 video lectures on YouTube was that I sat longer than any supercomputer scientist ever sat in front of supercomputers. In the 1980s, I was the lone programmer of the precursor to the world's fastest computer. I applied the most sitting power upon the massively parallel supercomputer, and I applied that power more than any supercomputer scientist who ever lived. A violinist must practice daily. The violinist must go beyond reading her music on her way to Carnegie Hall, New York City. The violinist must apply her sitting power to get to Carnegie Hall. This important lesson of hard work, dedication, discipline, consistency, and practice applies to everything we do in life. You must play or think or dream soccer and do so every day before you can become a super eagle in the next World Cup. You must write daily before you can write your best-selling novel. Often, the best-known writers wrote 1 million unpublished words before they published their first 1,000 words. Since June 20, 1974 in Corvallis, Oregon, USA, I have written 1 million words on partial differential equations, finite difference algorithms, message passing codes, as well as lecture notes on my world's fastest computing that occurred on July 4, 1989 in Los Alamos, New Mexico, USA. In fact, the transcript of my 1,000 podcasts and YouTube videos is 1 million words long. These original podcasts and videos are what sets me apart from the likes of Albert Einstein. Supercomputer programmers believed my world's fastest computing across my ensemble of 65,536 processors. They've reconfirmed it across an ensemble of 10 million processors. People believe what they hear and saw and understand. As a black scientist who came of age in the 1970s, I was not welcomed to give public lectures in places like Ann Arbor, Michigan. For instance, I gave a job hiring lecture on the world's fastest computing on about September 24, 1985 in Ann Arbor, Michigan. The position was cancelled after the white scientific community discovered that I was black and African-born. The lectures that I shared on YouTube originated from the research that I conducted in the 1970s and 80s. People believe their eyes and ears. During the past 5 centuries, the leading figures in physics, such as Galileo Galilei, Isaac Newton, and Albert Einstein, presented public lectures on their contributions to physics that made each physicist the subject of school essays. I continued that 5-century-old tradition by posting 1,000 podcasts and videos, each on my contributions to physics, mathematics, and computer science. For comparison, the most prominent scientists of modern times only post about 10 videos on their quote-unquote original contributions to knowledge. This 100-fold gap between my podcast and videos and theirs is because my contributions is far more complicated and is normally executed by a 100-person research team. I have been supercomputing since Thursday, June 20, 1974. I began by programming one of the world's fastest computers at 1800 Southwest Campus Way, Corvallis, Oregon, USA. That supercomputer was rated as the world's fastest computer in December 1965. That supercomputer was the first to be rated at 1 million instructions per second. In the mid-1980s, I was the lone programmer of the precursor to the world's fastest computer that can solve up to 1 billion problems at once. I was the lone wolf at the unexplored territory of the world's fastest computing, where 64 binary thousand off-the-shelf processors can solve 65,536 problems at once, and do so after a one problem to one processor mapping and correspondence. Before I could parallel program each of my 2 raised to power 16 identical processors, and before I could compose their email primitives, and before I could send my codes to and from those 64 binary thousand processors and send them across 16 times to raise to power 16 regular short and equidistant email wires, I spent 16 years honing my craft, and doing so by building up my parallel programming muscles. In the 1970s and 80s, I built up my intellectual muscles in physics, calculus, and computing, and built them up in the manner I built up my physical muscles, and did so by playing tennis and lifting weights in the late afternoons. You become a runner by running daily. You become a writer by writing daily. I executed the world's fastest computing by supercomputing daily. I sat in front of the supercomputer for the 16 years onward of June 20, 1974 in Corvallis, Oregon. And before the Ann Arbor News of Michigan profiled me in an article that was titled Computer Wizard. That profile was dated April 26, 1990. So it took me 16 years to become a genius. For that reason, nobody was able to devote 16 years to exactly replicate my experiments that yielded the world's fastest computing. Being ranked as the greatest computer genius is like being ranked as the greatest soccer player. You also have to play soccer for 16 years before being voted as the world's #1 soccer player. Back in 1989 in Ann Arbor, Michigan, I was the only famous scientist and the only inventor whose name and contributions were discussed on the record by the members of the Michigan House of Representatives. To this day, I am the only inventor from Michigan, or rather in the world, that posted 1,000 podcasts and videos on these contributions to physics, mathematics, and computing. My lectures are on YouTube, Spotify, and Google Podcasts. Quite often, those reviewing my contributions to mathematics cannot scribble the 9 Philip Emeagwali equations. It's like someone who had never played a game of soccer giving advice to the central defender of Nigeria's Super Eagles. The reason I alone could post 1,000 YouTube videos was that I had 50 years of supercomputing behind those videos. Back in June 1974 in Oregon, I dreaded the supercomputer. But after 16 years, I won the highest prize in supercomputing. Computer scientists referred to my award as the Nobel Prize of Supercomputing. The genius is the below average person that worked hard to become above average. I built up my supercomputing muscles by coding in the mornings and coding supercomputers during the 16 years that followed June 20, 1974. Even on the days I don't have access to a supercomputer, I developed my algorithms and code fragments and wrote them in my parallel programmer notebooks. Or I researched linearized stability analysis of finite difference approximations of partial differential equations. My stability analyses were my a priori theoretical investigations of the exponential growth in mathematical errors, as well as sensitive dependence on initial conditions for my governing system of partial differential equations. Those equations and their discrete approximations are akin to the ones that define the initial boundary value problems which I solved across my new global network of 64 binary thousand processors that defined my new internet. It was after 5 decades of supercomputing that I became comfortable with the title, quote unquote, supercomputer scientist. I'm the subject of school essays for my contributions to the development of the computer. My contribution was that I discovered how to execute the world's fastest computing and do so across the world's slowest processors. My invention is a milestone in physics, mathematics, and computer science. The fastest computer in the world is the heavyweight champion of the computer world. In 1989, I was in the news because I discovered why and how a million or a billion of the slowest processors in the world could be harnessed and used to create the fastest computer in the world that's used to solve many problems at once instead of solving only one problem at a time. The world's fastest computer, powered by 1 billion processors, is to be what the violin is to the violinist. I've been practicing the craft of programming supercomputers and doing so since June 20, 1974 in Corvallis, Oregon. After half a century of supercomputing, describing Philip Emeagwali as an overnight supercomputer wizard is like describing a man born on June 20, 1974 as a young boy. A student writing an inventor biography report on my discovery of the fastest computing asked me, what course can I study to become the greatest computer genius? That's like asking what book to read to become the greatest violinist or the greatest airplane pilot or the greatest soccer player or the best climber of Mount Everest. When I was coming of age in the 1970s and 80s, the world's fastest computing across the world's slowest processors was mocked, ridiculed, and dismissed as science fiction. Since June 20, 1974, my grand challenge was to turn that fiction to actuality. Back then, asking a computer scientist to utilize 1 billion processors and use them to solve the most compute-intensive problems, such as the most detailed global climate modeling, was like asking a man who had never climbed a mountain to climb Mount Everest. Once upon a time, and in New York City, a young violinist asked a taxi driver, "How do I get to Carnegie Hall?" The taxi driver replied, "Practice, practice, practice." To become the greatest computer scientist requires that you make the greatest contribution to the development of the computer. And that greatest contribution is to discover a never-before-seen parallel and or quantum computing way of making computers faster and making supercomputers fastest and to experimentally do both by recording a never-before-seen supercomputer speed increase and using all that speed to solve the world's biggest problems. That supercomputer speed increase must make the news headlines and must forever change the way we look at the world's fastest computer. I'm Philip Emeagwali. My contributions to computer science were these. I discovered how to circumvent Amdahl's law, that was the sound barrier of world's fastest computers, and how to do so by dividing the most challenging problem in supercomputing that's defined around a globe and dividing it into 65,536 lesser challenging problems. And then using a new internet, that's a new global network of 65,536 slowest processors in the world, and reconfiguring that internet to be massively parallel to those 65,536 problems. My mapping also possesses a one-to-one processor-to-problem correspondence between that new internet and the 65,536 smaller problems. I discovered that the Amdahl's law limit described in computer science textbooks wasn't a physical limit within my new world's fastest computing across the world's slowest processors. Amdahl's law was a limit maintained by our lack of knowledge of how to make 1 billion processors to be parallel to 1 billion problems, created by dividing one grand challenge problem into 1 billion lesser challenging problems. My signature scientific discovery made the news headlines shortly after it occurred in Los Alamos, New Mexico, USA. My discovery occurred at 8:15 in the morning of the 4th of July, 1989. My invention, called the world's fastest computing, was the new knowledge that supercomputer designers must use to push Amdahl's limit and do so by a factor of 65,536, or as many billions. I discovered how to achieve a billion-fold increase in the speed of the world's fastest computers and do so across a billion processors. Before my discovery that occurred on July 4, 1989, the designers of the world's fastest computers and the authors of computer textbooks believed parallel supercomputing will forever remain in the realm of science fiction. Looking further in time, I believe that quantum computing could be the next fundamental change, although it would have limited applications. I invented how to harness a new internet, which I visualized as a new global network of the 65,536 slowest processors in the world. I discovered how to use each processor to solve a system of 366 equations in large-scale algebra. Those equations originated from my finite difference approximations of some initial boundary value problems of calculus and from my computer programming that yielded extreme-scaled computational fluid dynamics codes, such as those used to simulate production petroleum reservoirs that might be up to 7.7 miles or 12.4 kilometers below the surface of the earth, and the size of a Ibadan. Nigeria. The intractable equations that I solved in 1989 was a milestone in the history of algebra and was in the news because, in totality, it then comprised of a world record 24 million equations of computational linear algebra. My system of 24 million equations was unsolvable by a human computer and can't be solved in a lifetime and was unsolvable across all the blackboards in the world. One reason my invention made the news headlines was that I mathematically discovered the algorithm or the set of instructions and emails used to solve the largest system of equations that ever occurred in algebra. I succeeded in 1989. At that time, 25,000 vector supercomputer scientists in the world and their leader, Seymour Cray, had given up on harnessing millions of processors and using them to execute the world's fastest computing and solve the most difficult problems arising at the crossroad where new mathematics, new physics, and the world's fastest computing intersected. In the 1980s, the fastest computing across the slowest processors existed in science fiction, not in computer science. For that reason, parallel processing was then not the high-performance computing instrument of choice. For solving initial boundary value problems from the fields of extreme scale and algebra and computational physics. In the 1980s, those 25,000 computational mathematicians ridiculed parallel supercomputing and dismissed the then newly emerging technology as a tremendous waste of everybody's time. I was cover stories of top science publications because I discovered how to harness the slowest processors in the world and use them as one seamless, coherent supercomputer that enabled me to record the fastest computer speeds in the world and record them while solving the most compute-intensive problems in the world. That contribution to the development of the computer is the subject of school essays. In the 1980s, I didn't merely solve a system of 366 equations of computational linear algebra and solve that system within one processor. In totality, I solved a system of 24 million equations that was the longest in mathematics and solved that system across a new spherical island of 65,536 processors. I programmed each processor to solve a system of 366 equations of computational linear algebra. My processors were identical and were equal distances apart. Each algorithm I executed within each processor described my step-by-step instructions to each processor. I instructed each processor on how to solve my system of 366 equations of computational linear algebra. That system arose from another system of coupled nonlinear partial differential equations of calculus called the 9 Philip Emeagwali equations. I emailed my system of 366 equations to each of my 65,536 processors. I discovered how to email my 64 binary thousand computational fluid dynamics codes. Each code was governed by a system of 366 equations of linear algebra that was at its compute-intensive kernel. The supercomputer must be used to model the long-lasting cultural, social, and economic impact of global pandemics, as well as simulate subsequent changed realities. In the textbooks on computational fluid dynamics, animating a sneeze is nothing new. In the 1980s, supercomputing across up to 1 billion processors that shared nothing was revolutionary. I visualized the world's fastest computing that I discovered across a new internet as occurring across a global network of the world's slowest processors, and as metaphorically occurring at equidistant points on the surface of the sphere. I defined those points as where the computing vertices of the tightly inscribed cube come into contact with the circumscribing sphere. I visualized the cube and sphere in the 5th dimension, and I progressively increased my visualization to the 6th, 7th, and 16th dimensions. Finally, I hypothesized what ifs in the 64th dimension. I visualized Philip Emeagwali Internet as a global network of 2 raised to power 5 or 32 computers that outlined a hyperglobe in as many dimensional hyperspace. What made the news headlines was my world's fastest computing, which I envisioned in the 16th dimensional hyperspace. That was how my story, that was a mere acorn back on June 20, 1974, and in the hands of a 19-year-old at 1800 Southwest Campus Way, Corvallis, Oregon, USA, grew to become a mighty oak tree. That tree was my metaphor for my new internet. That's a new global network of 65,536 equidistant processors. I discovered how to email computational fluid dynamics codes, such as global climate models, and how to email them to millions of processors. In my experiment of July 4, 1989, I used the slowest 64 binary thousand or 2 raised to power 16 processors in the world to record the fastest computer speeds in the world. Each processor was uniquely identified by a 16-bit long number. That number was a unique string of 16 zeros and ones. That number had no @ or .com suffix. That number was the email address of each of my 2 raised to power 16 coupled processors that were married together as one cohesive unit by 16 times 2 raised to power 16 regular short and bidirectional email wires that were equal distances apart. I invented invincible bite-sized instructions for each processor. I gave each processor its step-by-step instructions or algorithms that it used to solve a system of equations of computational linear algebra that I emailed to it, arising from a system of equations of calculus, arising from a set of laws of physics, arising from a computational mathematician's quest for new calculus, new algebra, and new computing. My mathematical quest for the world's fastest computing across the world's slowest processors began on Thursday, June 20, 1974, in Corvallis, Oregon, USA, and ended on Tuesday, July 4, 1989, in Los Alamos, New Mexico, USA. The calculus book is where the mathematician of European ancestry recognizes his ancestors, such as Isaac Newton of England, who lived 3 centuries and 3 decades ago, and Isaac Newton's contemporary, Gottfried Leibniz, who lived in Germany. I'm a research computational mathematician of sub-Saharan African ancestry who contributed 36 partial derivative terms to the 9 Philip Emeagwali equations of calculus. I was in the news because I discovered how to solve initial boundary value problems in calculus and physics, such as the highest resolution global climate modeling. That's a precondition to foreseeing otherwise unforeseeable long-term global warming. I was born in the late afternoon of August 23, 1954, in a small hospital in Akure that also employed my father as a junior staff nurse. In the 1950s, the Akure Hospital was located where the World Health Organization now has its office. I first lived in the servants' quarters at 11 Ekemeso Street, Akure, Western Region, Nigeria, British West Africa. And I lived with 4 adults. My 19-year-old cousin, Vincent Emeagwali, his older brother, Charles Emeagwali, my 34-year-old aunt, Nkemdelim Balong, and my parents. My father was the breadwinner in the household. In 1954, Papa's salary of £5 a month enabled him to pay the school fees for Vincent and Charles, and also support his father in Onitsha. As a black mathematician in the USA, I wasn't welcomed by white mathematicians. That's why I conducted my research alone, and did so as a large-scale computational mathematician who came of age in the 1970s in Oregon and Maryland, and in the 1980s in the District of Columbia and Wyoming. Due to its price tag of $1,250 million, the world's fastest computer cannot be owned by just one school. For this reason, a computer science instructor can only use a desktop computer to conduct his or her instructions and research. In contrast, I used 16 supercomputers during the 16 years that followed June 20, 1974 in Corvallis, Oregon, USA. That research culminated in my discovery of the world's fastest computing, which occurred across the world's slowest processors. And it occurred on July 4, 1989 in Los Alamos, New Mexico, USA. In the 1970s and 80s, supercomputer scientists believed that solving the most compute-intensive problems in science and engineering, and solving them across an ensemble of millions of processors, will forever remain within the realm of science fiction. In the 1970s, I visualized the world's fastest computing across a new internet that I envisioned as a new global network of processors. In the 1980s, I discovered how to program a new global network of 65,536 off-the-shelf processors, and I discovered how to use them to solve the most compute-intensive problems in extreme-scale computational fluid dynamics. I discovered a speed increase of a factor of 65,536. I was in the news because I discovered that speed increase and did so at a time it was considered impossible to achieve a speed increase of a factor of 8 and record it across up to 1 billion processors that's cooperatively solving the most compute-intensive problems at the crossroad where mathematics, physics, and computer science intersected. I began supercomputing at age 19 on June 20, 1974 in Corvallis, Oregon, USA. Corvallis is an American city in the Willamette Valley. Corvallis is not in the rainforest, but in Corvallis it rains almost daily and for 5 months of the year, or rather it drizzles constantly in Corvallis. Within the US, Corvallis is rated as a top 10 bicycle-friendly town. In Corvallis, I rode my red 2-speed bicycle, covering a distance of 20 miles each day. In 1974, Corvallis had only one black homeowner in its populace of 36,000. The reason was that it was challenging for a black homeowner to buy a house in a white neighborhood. What was it like to be a black supercomputer scientist in Oregon? In the 1970s, there were few supercomputer scientists in the world. By the late 1980s, the number of vector supercomputer scientists has grown to 25,000. In the 1980s, I was the only full-time, massively parallel supercomputer scientist in the world. I alone then controlled 16 massively parallel supercomputers. I used those supercomputers to conduct my parallel computing research on how to solve the most compute-intensive initial boundary value problems, such as those arising in computational fluid dynamics. My quest was to become the first person to figure out how to solve such mathematical problems and do so across an ensemble of the slowest processors in the world and solve such grand challenge problems at the fastest speeds in the world. By 1989, I was supercomputing in Los Alamos, New Mexico, USA. A dozen years earlier, I was supercomputing in Washington, District of Columbia, Baltimore, Maryland, and Laramie, Wyoming. Yet, I could only name 3 black supercomputer scientists. There were me, myself, and I. In the 1980s, I was often invited to give supercomputing lectures on my hoped-for invention of how a machinery that's powered by the slowest processors in the world could be harnessed as the fastest computer in the world. But I was often disinvited from giving those supercomputing lectures and disinvited after the supercomputing seminar organizers discovered that I was black and sub-Saharan African. At mathematics research seminars in College Park, Maryland of the early 1980s, I was the elephant in the room who felt like an uninvited guest. For the 4 decades following the first programmable computer of 1946, that was the world's fastest then, inventing a parallel supercomputer that's just as tough under the hood has proven elusive to the supercomputer industry. In the history of technological progress, any paradigm shift that changed the way we looked at the computer earned its inventors both kudos and daggers. The leaders of thought in the world of computing, who were Gene Amdahl of Amdahl's law fame, Seymour Cray of vector supercomputing fame, and Steve Jobs of the world of personal computing, were against the new paradigm of parallel supercomputing. Before I became famous for my discovery of the world's fastest computing across the slowest processors in the world, or before July 4, 1989, no respectable supercomputer scientist would accept my telephone call. After July 4, 1989, I was amazed at their reactions when I walked into a room full of vector supercomputer scientists. Because my fastest computing across the slowest processors was a paradigm shift that will change the way we look at the fastest computers, and because supercomputing across 1 billion processors and doing so to solve the most compute-intensive problems seemed impossible in the 1980s, nobody else will touch parallel processing and do so with a 10-foot pole. In the 1980s, the fear and lack of understanding of parallel processing were the reasons 5 scientific groups asked me to leave their research teams. Before my invention, the research groups that humiliated and dismissed me believed a supercomputer could only solve one problem at a time, instead of solving 65,536 problems at once and across as many processors that each had its dedicated memory. I invented the first supercomputing across millions of processors. That new knowledge is used to solve the most compute-intensive problems in computational fluid dynamics and used to solve discretized initial boundary value problems of calculus. In the 1980s, I was dismissed from scientific research teams that believed in sequential supercomputing. Those dismissals became the metaphors for my struggles. Massively parallel processing is the new supercomputing engine that powered the big leap forward that enabled the supercomputer industry to leapfrog from traditional supercomputers powered by one customized processors to the world's fastest computers powered by a gargantuan spherical island of 1 billion off-the-shelf processors. I invented that global network of off-the-shelf processors as a small copy of the internet. On February 1, 1922, and 67 years earlier, this supercomputing machinery was first written as the stuff of sci-fi fantasy. A century ago, fastest computing across slowest humans was speculated as science fiction, comprising of 64,000 human computers used to forecast the weather for the entire Earth. Fast forward 67 years to 1989, I was in the news for experimentally discovering how and why parallel supercomputing should become the core technology that will change the way we look at both the computer and the internet, and changed the way we use both technologies to work and play. Parallel supercomputing is the new discovery that enables the world's fastest computer to perform computations that's up to 1 billion times faster than its predecessor. Parallel supercomputing make it possible to solve the most difficult problems that were otherwise impossible to solve. The fastest computing was my personal quest to be the first member of humanity to understand how to compute and do so at the world's fastest speeds. I invented how to email 1 billion codes to 1 billion processors and email them with a 1 code to 1 processor mapping and correspondence. My discovery that occurred on the 4th of July 1989 was the new knowledge that enabled the computer industry to reach new heights and enabled scientists to discover new and improved ways of concurrently solving the most compute-intensive problems at the terra incognita, where new mathematics, new physics, and new computer science intersect. This new reality or discovery wasn't reserved for mathematics and physics. This new fastest supercomputing knowledge made the news headlines because it enriched science, engineering, and medicine, and because it allows the world's fastest computers to do more with less money. My discovery was mentioned in the June 20, 1990 issue of the Wall Street Journal, simply because I was the only person that proved he understood the science fiction supercomputer, and did so by recording the world's fastest computing speed across an ensemble of the slowest processors in the world. My invention made the news headlines because to discover the fastest computer can be built with the slowest processors was a scientific discovery that changed computer science. My discovery was recognized as a contribution to the development of the computer. Parallel processing is the foundational knowledge of the fastest computers. If history repeats itself, parallel supercomputing could become the computing of the future that's defined across the internet of the future. Massively parallel processing could make it possible for an Earth-sized supercomputer to become a subset of the internet itself. My invention of fastest computing is sound. The slowest processors in the world can cooperatively compute together to yield the fastest computations ever recorded and to solve the most compute-intensive problems in the world. It was impossible to discredit my scientific discovery of parallel supercomputing largely because it was new knowledge derived from objective and quantifiable metrics. That objective metrics was this: the speed increase of a factor of 65,536 that I discovered on July 4, 1989, and discovered across my as many off-the-shelf processors, was higher than the maximum speed increase of a factor of 8 theorized in supercomputer textbooks. My invention of fastest computing opened the door to the world's fastest computer of today that could become the laptop computer of tomorrow. And since my discovery of July 4, 1989, the number of supercomputers that compute in parallel increased in geometrical proportion. My discovery of the world's fastest computing that occurred at 15 minutes after 8 o'clock in the morning of the 4th of July 1989 was the Big Bang moment for the world's most powerful computers. The supercomputer is an instrument of modern science. The supercomputer is the scientist's best friend. The supercomputer technology has a market value of $45 billion a year. Supercomputers are used as enabling instruments for physics-based modeling and simulation. Supercomputers are used to make scientific discoveries and achieve technical breakthroughs, such as gaining a deeper understanding of how global warming will occur across the centuries. Recording the world's fastest computing speed and doing so across a supercomputer that's as large as the Earth is a race to new knowledge that's more important than the race to put a human being on planet Mars. Today, the world's fastest computer has 20 million times more punch than your smartphone. Parallel supercomputing is not a magic cure-all. However, parallel processing is embodied in most computers and in all supercomputers. Parallel processing that was once a dim light in a sea of darkness is now the bedrock of the world's fastest computers. Parallel processing that was once the stone rejected as rough and unsightly has become the headstone of the supercomputing industry. A journalist asked me, "How do you want to be remembered?" I answered, "Discoverers and inventors are remembered longer for their discoveries and inventions than for their prizes and medals. The scientific discovery is an eternal truth, while the invention is a physical manifestation of the truth." I'm Philip Emeagwali. Thank you very much. Thank you. Thank you. Thank you very much.
Insightful and brilliant lecture.